In this lesson, we're going to look at rational functions. First, we're going to start looking at the definition of rational functions. So, a rational function is essentially the quotient of two polynomial functions. The official definition is written here. A rational function, let p of x and q of x be polynomials where q of x does not equal 0. A function f defined by f of x equals p of x divided by q of x is called a rational function. So we have the quotient of two polynomial functions where the denominator cannot equal 0. That should make sense because we've talked about this before, and I'll talk about it again. We cannot divide by 0. So dividing by 0 is undefined. We've discussed this in terms of multiplication and how it breaks the rules of multiplication. And so therefore, we know that the denominator cannot be equal to 0. So these graphs usually have either vertical or horizontal asymptotes. These are dashed lines that the graph approaches. So one thing we'll find out though about this is that there's a difference between our vertical and horizontal asymptotes and our slant asymptotes. And we'll look at the differences between those and how we find out what those values are. Two of the most popular rational functions that we've seen before as parent functions are f of x equals 1 over x and f of x equals 1 over x squared. So we have the graphs of these two rational functions. They should look familiar from the chart that we saw in the beginning of the semester of our parent functions. So we can also perform transformations on these parent functions. Remember that when we add or subtract something to our x value, that shifts our graph to the left or to the right. If we add or subtract something to the entire function, that shifts our graph either up or down. So I can take the information that I have here and I can graph each of the following functions using transformations. So f of x equals 1 over x plus 2 minus 1. That's going to shift left. That's going to shift the graph 1 over x left by 2 and down 1. So two of the points that we had very clearly on this function were 1, 1 and negative 1, negative 1. So I'm going to take 1, 1 and I'm going to shift left 2 and down 1. And that plot's right there where I'm putting a blue dot. Negative 1, 1, shift left 2 and down 1. Our asymptote, which I will do in a light gray, is going to, we have a vertical one here at x equals negative 2. Notice we've shifted left 2, so our original asymptote in the parent function was at 0, x equals 0, and so now our asymptote has shifted left 2 to be at negative 2. We have a horizontal asymptote. Our horizontal asymptote originally was at y equals 0. And so here our horizontal asymptote will shift down by 1 and will be here. So then we can draw our graph. I will draw it in purple. It goes upwards and approaches that asymptote here and here, and it goes from here to here. We can also talk about the domain and the range of this function. The domain is all x values except for negative 2. So the domain would be from negative infinity to negative 2 with parentheses unioned with negative 2 to positive infinity. The range, which I'll write in red right here, the range of this function is all the y values that it passes through, which would go from negative infinity to negative 1, because that's where our horizontal asymptote is. There's a break there, and then we union that with negative 1 to infinity. So because we have parentheses here and here and here and here, we can see that it doesn't ever touch or include negative 2 in our domain, and it doesn't include negative 1 in our range. We can do the same thing for this next one. Now notice the next one we have g of x equals negative 1 over x squared plus 3. If you go all the way back to our lesson 2 notes on transformations of functions, you'll recall that this negation right here is going to cause a reflection across the x-axis. And you can also look at the order of performing transformations, which would be, remember, horizontal shifts, then horizontal or vertical stretches and shrinks, reflections, and then last but not least are vertical shifts. So in this case, we're going to take the original function 1 over x squared, which is above right here, and it's going to be reflected over the x-axis, and then it's going to shift up by 3, because this represents a vertical shift upwards. So let's go ahead and do that. So the first thing is, on the original graph, there was the point 1, 1 and negative 1, 1. And so that point is going to be reflected over the x-axis. So 1, 1 would now be at 1, negative 1. And negative 1, 1 would now be at negative 1, negative 1. So there's a shift there to there. Okay. And then we need to then shift that point upwards. 1, 2, 3. 1, 2, 3. Our asymptote would stay the same with the reflection, but then it would shift up 3. So our original asymptote here was, for the horizontal asymptote, was the x-axis. So the new horizontal asymptote will be at positive 3. Since there were no horizontal shifts, our vertical axis would stay, or our vertical asymptote would stay the same. And so the new graph, which I will graph in purple, would look like this. And remember that these red points are just showing the intermediate steps of the reflecting over the x-axis and then the shifting up by 3 to the blue point. So again, we can use the rules of transformations of graphs that we saw in lesson 2 and apply them to parent functions when our rational functions actually match our original parent functions that we saw a long time ago. The next thing we're going to look at is identifying vertical asymptotes. So what you're going to do is, after possibly simplifying the function through factoring, we then set the bottom equal to 0, and that tells us where our vertical asymptotes will be. When you have something in the numerator that cancels out with a piece of the denominator that involves x, that creates what's called a hole. And so if you have holes, that gets represented with like a little open circle on that point in the graph. Okay, and so just know that if you do end up factoring and simplifying through factoring, you will end up with holes in your function. But let's start off talking about finding our vertical asymptotes. Now, we looked at these parent functions. These parent functions had vertical asymptotes at x equals 0. Because if you think about it, if I take my denominator, and this one, my denominator is x, and set it equal to 0, that's my vertical asymptote. Same thing here. If I take my denominator, which is x squared, set it equal to 0, well, the square root of 0 equals 0. So this is my vertical asymptote. So what we're doing is we're doing the same thing here. Remember that vertical lines are written in the form of x equals something. X equals a constant. Like x equals 0, x equals 10, x equals 2/3. These will represent our vertical asymptotes. A vertical line is an x equals equation. So let's try this first one. First, we're going to factor it just to check and see if anything cancels. So two numbers that multiply to get -5 and sum to get -4. So that's going to be x minus 5, x plus 1. Neither of those factors will cancel with x minus 3 in the numerator. And so therefore, I take both of these pieces to find out my vertical asymptotes. So I'm going to do x minus 5 equals 0 and solve for x. So add 5 to both sides. We get x equals 5. And then we're going to do x plus 1 equals 0. Subtract 1 from both sides, and we get that x equals -1. In this case, I have two vertical asymptotes, x equals 5 and x equals -1. The next one, we have, we're going to factor. Also, when you factor it, it also allows you to easily set up and solve for your asymptotes because you have your factors already ready to go, set them equal to 0, you're good to go. This one, two numbers that multiply to get -3 and sum to get -2 are going to be -3 and +1. So then I see that I can cancel out x minus 3 from my numerator and denominator, which leaves me with 1 over x plus 1. Now the x minus 3, set that equal to 0, we get that there is a hole at x equals 3. So that would represent a hole, but for our vertical asymptote, we would take our denominator, x plus 1, set that equal to 0, subtract 1 from both sides, we get x equals -1 is our vertical asymptote. On this one, we're going to take our denominator and set it equal to 0. So that's going to be x squared plus 25 equals 0. Subtract 25 from both sides. We get x squared equals -25. This should be a throwback because we get positive or negative, square root. So we get x equals plus or minus square root of -25, which equals plus or minus 5i. So it has an imaginary vertical asymptote, so it would not have a vertical asymptote. It's not possible for this to ever, this will never equal 0. Which means there will be no values for my domain that would be undefined and cause a vertical asymptote. All right, moving on to identifying horizontal asymptotes. To do this is a lot different. So for the first one, you had to actually solve and set your denominator equal to 0 to find where your vertical asymptotes are. Finding horizontal asymptotes, it's just 3 rules you need to know. The first rule is, well, the first thing you need to know is that you're comparing the degrees of the numerator and the denominator, okay? If the degree of the top is less than the degree of the bottom, then the horizontal asymptote is at y equals 0. So we saw this in the example for 1 over x and 1 over x squared. The degree of the top is 0, the degree of the bottom is 1, the degree of the top here is 0, the degree of the top or bottom here is 2. We have a horizontal asymptote in the situation where y equals 0. Okay? If the degree of the top is greater than the degree of the bottom, then there is no horizontal asymptotes. And if the degree of the top is equal to the degree of the bottom, then the horizontal asymptote is it's written as a fraction, y equals the leading coefficient of the numerator over the leading coefficient of the denominator. So, all right. So what we want to do here is we want to look at the degree of the top, which on this one is not 0. I don't know why I wrote 0. The degree of the top on this one is equal to 1. The degree on the bottom is equal to 2. So the top is less than the degree of the bottom. So this has a horizontal asymptote at y equals 0. On this one, the degree of the top is 2. The degree of the bottom is 2. The degree of the top and the bottom are equal, so their horizontal asymptote is at the equation. I guess you could think of this as the equation of a horizontal line at y equals 3, the leading coefficient of the top over the leading coefficient of the bottom, which is 1. So 3 over 1 is just 3. So the horizontal asymptote on this one would be y equals 3. On this one, the degree of the top is 3. the degree of the bottom is 2. The degree of the top is greater than the degree of the bottom, and so therefore there is no horizontal asymptote. So HA is standing for horizontal asymptote. So finding the horizontal asymptotes, I think, is a lot easier than finding the vertical asymptotes.